I'm the Senior Communications Manager here at Beyond Zero Emissions. So today we're going to be talking about our main discussion group, the Hunter, the electric motor of the Australian economy. That's the aim anyway. So I'm very keen to introduce our guests, but everyone's coming through. Yep. I'll just start by doing an acknowledgement. I'd like to acknowledge the Bunurong people of the Kulin Nation. They're the traditional custodians of the land on which I live and work in the area spanning the Mornington Peninsula and Western Port in the southeast of Melbourne. I'd also like to acknowledge both the Awabakal people and Worimi people, the custodians of the land around Newcastle and Hunter Valley, where many of our guests are joining us from today and where our attention is currently focused. I pay my respects to elders past and present and acknowledge that sovereignty was never ceded and that it always was and always will be Aboriginal land. I'd like to extend my respect to any Aboriginal and Torres Strait Islanders peoples joining us this afternoon. And if you'd like to do so, please share the country you're joining us from and the traditional owners you acknowledge in the chat function. So just a little bit of housekeeping. We'll use the chat feature for the Q&A. I'm going to introduce our guests and run through the three presentations first. So perhaps keep your questions towards the end of the hour, otherwise they will get lost in the feed. Please keep everything respectful as always. And a reminder that the discussion will be recorded and posted on the events page of the Beyond Zero Emissions website after. So thanks for joining us. I will kick off by introducing Sam Meller. Sam is the Beyond Zero Emissions Engagement and Project Lead in the Hunter Valley and was the lead author of the Hunter case study in our Million Jobs Plan. She has done pioneering work on renewable energy export since 2011, including as project leader of the acclaimed pre-feasibility study that investigated high voltage direct current as a potential renewable energy export and diversification pathway for the Pilbara region of WA. Sam is also a founder and director of Pilbara Solar, and Sam is a brilliant connector and communicator. For those of you who were lucky enough to attend the recent Hunter Innovation Festival, you'll have witnessed firsthand her fantastic ability to bring together industry leaders and to join forces towards a common goal. That goal at the moment is our first renewable energy industrial precinct in Hunter. And I'll let Sam go into more detail on that.
Okay, thanks, Nicole. Can you hear me okay?
Great.
I feel very humbled by that introduction. Thank you very much. So I'm just going to share my screen now. And I'm going to do a quick overview of the Renewable Energy Industrial Precinct project, which is Beyond Zero Emissions major project at the moment. But I imagine that most of the people in this room are quite familiar with this project. So I want to keep it quick so we can move to the work of Dr. Jessica Allen and Dr. Nicholas Guriev. I'm really fortunate. I have a really great job in that I get to talk to people and industry and researchers on the ground here in Hunter. And in the Hunter, we have two big research institutions, and that's the University of Newcastle and the CSIRO. And today we're really fortunate because we're going to get a window into some of the work that's going on at the University of Newcastle. So, the Renewable Energy Industrial Precinct, as you all know, is our major project in Beyond Zero Emissions at the moment. So quickly, what is a Renewable Energy Industrial Precinct? It's a cluster of manufacturers powered by 100% renewable energy. And the Hunter is just so ripe for this to happen because we're located within a renewable energy zone. The Hunter has been announced as a renewable energy zone, and we're connected to two really big renewable energy zones that are in development, the Irana Renewable Energy Zone and the New England Renewable Energy Zone. And it's going to be a centre for manufacturing, and we're going to change the way we export energy. We're going to start embodying energy in products and having energy intensive exports, as opposed to the way we export energy at the moment, which is loading coal and gas on ships. We're going to diversify. So why are we going to do this? Because that's where the global market is headed, and we need to enable the Hunter to remain a significant global energy hub. We know that companies like Toyota, Coca-Cola, Apple, I mean, the other day it was Coles, there's a new announcement every day that companies are trying to decarbonise, and one of the ways they can do that is take the emissions out of the supply chain. And this is a huge opportunity for the Hunter and a huge opportunity for Australia. But as I'm going to talk to you, we're very well positioned to do this. So this is just a little bit of a drill down of what a renewable energy industrial precinct is. So if we start there on the bottom layer, the renewable energy zone aspect of it, we've got all that happening. It's already here. We've got fantastic transmission. There's pumped hydro projects in development, offshore wind, the renewable energy zones, the utility scale storage. Nicholas can talk to us a little bit more about storage. If we go into the regional level, the Hunter has all this fantastic legacy research from legacy infrastructure on a regional level from the coal industry, transmission, port, rail, and just today in the Newcastle Herald, there's a discussion of a project that will put in a hydrogen pipeline. So moving up to the third level there, what we are going to create locally is the Renewable Energy Industrial Precinct. It begins with, the clustering of industry together. And I can tell you, I'm talking to businesses in Hunter every day, and there's a real appetite for that, for the collaboration, for learning from each other. I sit in a clean tech hub, and this clustering together is really beneficial for everyone, and we all recognise that. So the hydrogen network, again, that's something that's now being put on the table. The heat networks, we've got, that's something that Jessica can address in her industrial ecology research. We have the circular economy that's being driven by Hunter joint organisations, and there's a number of businesses up here now focusing on circular economy and commercialisation. The University of Newcastle commercialises, offers support to PhD students to commercialise, and we've seen two really great innovative PhDs showcased through BZE, the diffuse energy and MGO thermal bricks. So it's really about pushing the research and innovation out into our economy. So if we get up onto the manufacturing level, this is really how pulling all the reaps together. I'm sitting right now in the TAFE at Hamilton with the focus on innovation and industry and training. We have in here in the Clean Tech Hub, it's all about smart monitoring and the grid services, and I'm working with Switched-In, which is doing a lot of that, and now the smart monitoring is just happening more and more. Diffuse energy monitors every wind turbine they have, and so we're more than able to do all of that. In the Renewable Energy and Industrial Precinct, BZE describes it that we have 10 years for the energy intensive companies that want to participate in the REAP to transition their process to electricity, to electrify. And that is an understanding that it's a complex thing to do for a manufacturer that's operating. But again, Jessica has some great discussion around that. And bring it all together with efficiency is something that can happen with a REAP. For example, using waste heat as feedstock, and it's another efficiency that helps us be more competitive. And what the outcomes for that, we believe, in the Hunter will be is massive new export opportunities as we take the things that the Hunter is really known for, and that's batteries, mining equipment, aluminium and steel. We want to bring back the green steel process here and create these zero emissions products and really promote Australian innovation and have a thriving economy. So that's what a renewable energy industrial precinct is going to do here by 2030. And why the Hunter? Because we're fabulous. We have everything that we need to do this, and we're already starting to do it. So I just want to talk to you about now what Beyond Zero Emissions is doing. Beyond Zero Emissions is briefing the federal government and pitching the Renewable Energy Industrial Precinct policy to the federal government, and we're aligning with what the federal government is already doing, their modern manufacturing strategy, their hydrogen strategy and their low emissions technology strategy. And we're really focusing in on the Hunter and Gladstone, but there are a number of opportunities around Australia. But how our work, I'm on the ground in the Hunter to create a renewable energy industrial precinct with the people of the Hunter that will work for the Hunter. So we're working really on these two levels of the enabling federal policy and funding. We just need the funding unlocked, but we're driving the precinct anyway. So we have, like I said, I'm talking to researchers and businesses in the Hunter all the time. We've launched a website about repowering manufacturing. We're showcasing some of the brilliant innovation that's coming out of here. And we're asking for expressions of interest and statements of support for the renewable energy industrial precinct. So we're gathering all that support by June 30 together, and then we're going to present this as evidence to the federal government that there is demand, there is collaboration, and we can do this. And then after, about 6 weeks after, in early August, for those businesses and organisations that have lodged an expression of interest or a statement of support, we'll be having a collaborative sort of closed door planning session to take it to the next level. So that's all from me. I'm going to hand you back to Nicole, and I just want to thank everyone for the support that you've given us here in the Hunter, and I feel really excited to be here enabling a discussion with the researchers at the University of Newcastle, Jessica and Nicholas. Thank you.
Thanks, Sam. So much happening, so it's wonderful to hear. We'll now introduce Dr. Jessica Allen. She is the Senior Lecturer in Chemical Engineering at the University of Newcastle and a recipient of an Australian Research Council Discovery and Early Energy Researcher Award in 2021. Sorry, that's a mouthful. Her research combines electrochemistry and engineering with interests spanning a wide range of low emissions energy technologies, including renewable energy, energy storage, both thermal and electrochemical, as well as carbon capture and utilisation. She is the Hunter's homegrown expert in all of the technologies coming out of the University of Newcastle, and looks at how it all fits together in a neat industrial ecosystem. Over to you, Jessica.
Great, thanks for having me, Nicole and Sam and Beyond Zero Emissions. Great to be here today. So I would like to share my screen here and talk a little bit about a couple of things that are happening here at the University of Newcastle and a bit about me. I'm just going to talk about two examples of renewables driven manufacturing but I do have a range of different things that I'm interested in. In particular, I'm going to talk about integrating renewable energy outputs with industrial processes today. And I'm going to be relatively quick about it because we only have 10 minutes. So I'm looking forward to some detailed questions at the end if I skip over anything you're interested in. So I'm not going to talk about this because Sam already covered it so perfectly and our slides align almost exactly. So I'll move on to the next one. And the first manufacturing opportunity that I want to talk about for the Hunter is steel. So green steel or decarbonised steel. And the two are a little bit different, which I'll show you today. So there's an opportunity for Australia to be involved in green steel. So we exported, we made 930 million tonnes of iron ore in 2019, but we only produced 5.5 million tonnes. We could have made 580 million tonnes of steel. So we've exported all of this iron ore. And in doing so, we're basically exporting our carbon emissions. That's those scope 3 emissions that Sam was talking about that companies and industries are becoming a lot more aware of. So currently there are 3 main methods to make steel globally. The dominant technology is blast furnace, which is about 70% of technology. There's a little bit of overlap between the blast and electric arc furnace, which is why the numbers don't quite add up there. Then we've got the electric arc furnace, which is mostly through recycled steel production. And then the final one is a new emerging technology, which is the direct reduction method. It's about 5% of production at the moment. So blast furnace technology, just briefly talking about it to give you an example of how we actually decarbonize this technology, because it's a little bit more complicated than just using green hydrogen, which is what green steel is generally thought of. You just, instead of using coal, you use hydrogen. Doesn't fully work that way, and in particular with the blast furnace. So a blast furnace uses coal in 2 different ways. So it uses a solid coking coal as an input, and it provides physical structure, and it also provides a bit of heat within the furnace. We also use pulverized coal, which goes in the bottom and provides a gasification agent. So it provides carbon monoxide, which is then the reducing agent in the iron making reaction. So, and both of these reactions here, so iron being Fe, is the iron that we want out at the end, and that sort of becomes a molten iron product that trickles through that solid layer, and then we also have a slag at the end. So in this process, basically we're turning iron oxide into iron, and we're stripping off the oxygen with carbon monoxide, okay? And what you get out at the end is carbon dioxide. Now in a blast furnace, both of these are generating heat, and we also tend to need a little bit of extra heat in the bottom. If you want to decarbonize this technology, there are a few things that you need to do. So one of them is replacing that carbon monoxide component with hydrogen. So green hydrogen, preferably from renewable electricity and water splitting. So the green hydrogen can go in the bottom. We'll also probably need still a carbon component in the bottom to provide carbon monoxide. And this is because the 2 reactions are very different. So you can use hydrogen to strip away oxygen in iron oxide and you make water. But unfortunately, this reaction requires heat. So it's a heat input rather than an output like we have with carbon monoxide. So that means we need a lot more heat to be put into the furnace because it's not going to be generating its own heat. We also can't completely get rid of the coke or that solid component going into the furnace. There has been some work on doing bio-derived blends, but the amount of biomass that you would need to replace coking coal is just not really realistic. So in the end, a decarbonised blast furnace will have recycled gases to provide as much heating as possible to make up for the fact that we've got that hydrogen reaction, so needing heat, and it will also need some carbon capture and storage. It's also probably going to need a bit of extra renewable electricity to provide heat and to decarbonise all of the auxiliary components, so taking over completely all of the electricity. The other method that I'm going to talk about is the one that has the biggest opportunity for green steel and for decarbonising. So you can see in the blast furnace that this is decarbonised, it's not green. So it still has a coal component involved in that steel making process. And this is what the dominant technology is and what is still being made and produced and installed today. So it's still a dominant technology. But this is a new one that's emerging. So this is direct reduction method. Now it's quite different in a number of ways, and I don't want to confuse everyone with all of the technical details in only 10 minutes, so I'll just give you the highlights. So the idea in this is that instead of dumping the iron oxide and all of the stuff that you dig out of the ground, which is what we do in the blast furnace, so the coke and all of the gangue it's called, so all the stuff that comes with the coke is dumped into the blast furnace. In this furnace, we want to firstly separate that as much as we possibly can to get a more concentrated iron oxide. That is then hit into a direct reduction furnace. And this works very differently to a blast furnace, and it's actually a gas and a solid interaction with the iron oxide. The reactions are still the same though. So we've got iron oxide and hydrogen with a heat input, and you'll also have some carbon monoxide, because at the moment this technology is commercialized using natural gas or steam coal gasification. So both of those are used to provide both hydrogen and carbon monoxide into this direct reduction furnace, which then has a balance of the heat being made and heat being used. After it goes through the direct reduction furnace, it goes into an electric arc furnace. And that's because in this furnace, we don't get to the high temperatures of the blast furnace. So the iron doesn't become molten. It becomes something called sponge iron, which then needs to be put into another electric arc furnace. So in this case, we need a fair bit more electricity for the process. So it is an electrification of sorts. So we're going to more electric energy in making the iron molten, and also in that sorting of the ore beforehand, because you really don't want to be putting all of the gangue in through here into the electric arc furnace, because then you need way more electricity, which is why you do the separation at the start. It's an optimization process there. So to decarbonize this technology, it has a better fit with hydrogen because it is a gas and a solid reaction. So in this case, we replace as much of the electricity as we can with renewable electricity. And then we also potentially move towards a hydrogen rich or a hydrogen pure component. At the moment, it's been estimated that about 70% of the hydrogen from methane reforming can be replaced with green hydrogen without significant modification of the process. So in that case, you would still need carbon capture and storage at the end, but you could decarbonize a large amount of the upfront hydrogen that you need. The 100% hydrogen still hasn't been demonstrated. It's in sort of design stage, moving towards pilot and hopefully being commercialized towards more 2030, 2040. There's a couple of companies, I think Hybrid are looking to have a pilot demonstration unit by 2030, looking towards more large-scale commercialization towards 2040 and 2050. So I hope that wasn't too quick and technical for you, but definitely happy to go back. Just the sort of outcomes from this is that 100% green hydrogen isn't yet technically demonstrated, but we can do up to 70% with the direct reduction process without significant modifications. These processes need large-scale generation of hydrogen. So it's a lot of hydrogen. Like the amount of hydrogen it needs is almost mind-boggling to do this sort of stuff. And it seems unreasonable when you write it down on paper, but with the scale of green hydrogen projects that are being announced and that are being put into place now, it starts to become a lot more reasonable. So we also are probably going to need a fair bit of storage for these green hydrogen based projects, partly because when you have a large industrial process that has a feedstock like this, it needs a contingency. So if something happens and it doesn't have that hydrogen it needs anymore, it needs a couple of hours of storage. And when you're talking about hundreds of thousands of tons of hydrogen, that can be quite substantial. So that's a bit of a challenge that needs to be thought about when doing these sorts of projects. And it's not just about hydrogen. So making as much hydrogen as we can with renewables is part of it, but we also still need the renewable electricity for the process as well. So both of those things are needed. We should have cost competitive green hydrogen by 2030 if all of the projects in the pipeline at the moment actually follow through, but it's not currently cost competitive. And it's still likely that we're going to need some aspect of carbon capture and storage on these technologies, especially thinking about how long it takes to build new capacity. And if we want to have a truly zero or net zero industry with green steel, we're going to have sort of a balance of practicality on those, especially if we want them in a shorter time frame. So that's a little bit about green steel. How am I on for time? That was my full 10 minutes, I think. So just briefly, my other project that I spend most of my time on really is about making materials and not emissions through renewable manufacturing. So the idea is that with concentrating solar thermal, we make heat and electricity. And electricity is useful, but it's also kind of cheap, and concentrating solar thermal energy is a bit more expensive to build. So it can't really compete with photovoltaics when you're looking at them next to each other, but it has something that PV doesn't, which is heat. So if we want to have a useful exportable product from concentrating solar thermal, then we need to make use of both the heat and the electrical component. And often concentrating solar thermal technologies will use molten salts for energy storage. And I've come up with a process design with colleagues at the CSIRO that takes advantage of all of these different aspects. So the production of heat, electricity, and the use of molten salts for storage. And this process does a carbon electrolysis reaction and generates carbon, which is a high quality, high value carbon material. It takes in carbon dioxide and it uses renewable energy. The carbon that we've made is very interesting and has a lot of very unique properties, which I won't go into, but we have found that it's the best possible carbon for sodium ion batteries, which are the next generation sustainable battery technology coming up. So it has a very high value application there. And basically the idea behind this is to solve multiple problems. So once we've completely electrified everything, put renewables on to make that electricity, we need to mop up all of the leftover emissions. And when you're on a small scale like this, technologies like this become feasible. They're not feasible to plug onto the end of what we've got right now. You cannot do it at that scale, but at a smaller scale, making an advanced product, then suddenly carbon capture and utilization and conversion into high value and stable products becomes very useful. And so I'll be working on this technology over the next few years, hoping to continue developing. And it's also a nice, has a nice synergy with renewable energy industrial precincts, because it's an example of industrial ecology. So taking the waste product of one manufacturer and turning it into a valuable product that another manufacturer could use. So you take an emission from, for example, in the Hunter, from aluminium production, making carbon dioxide, we turn that into a battery component that can be used by somewhere like Energy Renaissance, maybe, who have put up the world's first, Australia's first lithium-ion manufacturing facility. And it's just all connected together in a nice little symbiosis. So thank you. Sorry for rushing so much at the end. I talked too much about green steel, but looking forward to some questions at the end.
That's fine. I think there will be plenty of questions for you, Jessica. It was a great presentation and I learned a lot about those processes. I hope that we'll be able to share those after the session, because I feel like people would love to, get into a bit more detail on all of the technical aspects that you've just shared. So thank you. And we'll come back to some questions that are already coming through. So I'll just now introduce our third speaker, Dr. Nicholas Guriev. He is a multidisciplinary researcher focused on utility scale renewable energy storage, including Australian battery technologies and power to X with green hydrogen. I'll let him explain to you what that is. His work seeks to identify opportunities for these technologies to enable a responsible energy transition, such as secure fuel supplies and sustainable resource ecosystems for hospitals. He is a founding member of the NERA-backed Hunter Hydrogen Technology Cluster and is a past director of the Australian Institute of Energy. Nicholas, thank you so much for joining us. Over to you.
Thanks very much for the introduction, Nicole, and really happy to be here talking to all of you, because BZE's work really fits in with my research. I'll just share my screen and tell you a bit more about that. Alrighty, so I'm based at the University of Newcastle, along with Jessica, under Professor Badad Mohtaderi in the Priority Research Centre for Frontier Energy Technologies and Utilisation. I'll just tell you a little bit more about myself and my background and why I'm here doing what I'm doing. I'm a mechanical engineer, and my grandfather was a mechanical engineer who designed high pressure steam systems for coal-fired power plants. And I've had a bit of experience with large fossil fuel systems myself as a marine engineering officer in the Navy, and got to tour a coal plant not so long ago, which was really interesting given my family history. What I'm interested in as the next generation is wind and solar and what we do with those. Looking at energy storage, I did my PhD at UNSW on flow battery technology, which I'll explain a little bit more of. And now I'm looking at green hydrogen under the umbrella of Power to X, which is converting renewable energy into all kinds of things. I'll explain more as I go. Starting with REDOX flow batteries. The vanadium REDOX flow battery is an Australian technology invented at UNSW. And the cool thing about it is it separates the storage capacity, so the kilowatt hours or megawatt hours, from the kilowatts and megawatts, the power conversion, so the rate at which you can convert energy. So they're really good for grid energy storage, which has been recently recognized by the Secretary of Energy in the US, and a ARENA-backed demonstration in South Australia for making a dispatchable solar plant. So the tanks store the energy in electrolyte. The cells and stacks of those convert the energy. And it's the cells that I concentrated on for my PhD research. Basically, they're two half cells with fluid flowing through them, separated by exchange membrane, and with an electrical circuit around, external electrical circuit. So charging the battery, you put electrical power in, and change the chemical state of the electrolyte. And then you can reverse that to get power back. So it's a reversible process, a battery, but operates more like a fuel cell than a battery in your phone. What I did for my PhD research was modeled that on supercomputers. Modeling the fluid flow and the electrochemistry is frustratingly resource intensive. And then once I had some interesting designs from playing around with the different architecture of the cells, 3D printed some stuff and tested them in the lab, and then played around with some different designs with toroidal cells to make some batteries that look like a battery that we know. The problem with batteries is they're a great solution for lots of things, but not everything. Their energy density, both in terms of weight and volume or size, is still much lower than comparative things that we use for example, airliners, jet fuel, kerosene, gasoline, and other applications. So that led me to my current role looking at renewable hydrogen. Fortunately for me, there's overlaps with my PhD research. Renewable hydrogen is created from electrolysis, as Jessica was talking about. Here, it's very similar to how a flow battery works. With the flow cells, you're putting in electricity, you're splitting water and moving ions around. And then you can reverse that reaction. You can create reversible fuel cells, but it's generally done in another piece of equipment, a fuel cell, and you reverse that reaction to get power out. We've been doing that on site at the University of Newcastle. Bedad and my team have been using solar power to split water that we've extracted from the air with an atmospheric water generator, and technology Bedad developed labeled as the atmospheric water generator. And then we recently demonstrated that in a vehicle. We put that into a Hyundai, and I very happily got to drive that around. The problem with all this, as Jessica alluded to, is it's quite expensive. We want to directly electrify everything we can, because that's generally the best option. But there are some applications like chemical feedstock, steel, and long distance air travel, for example, that currently we just don't have the technology to directly electrify. And that's why I'm doing techno-economic analysis at the moment, looking at opportunities of how we can make this commercially viable now. And this really comes back to BZE's work with renewable industrial energy precincts. Hydrogen by itself very expensive, much more expensive than natural gas, for example. If we improve the capacity factor by firming renewables with something like a flow battery, we can bring that cost down by utilizing the electrolyzers more. But then we also produce oxygen from splitting water. And if we use that in something like a hospital, then we can actually generate hydrogen at a price that's competitive with natural gas for heating and power generation. Similar approach to looking at synthetic hydrocarbons. So power to hydrogen or power to gas sits under the umbrella of power to X, which is converting renewable energy into all kinds of things. One of those things being synthetic fuels. So we can actually make kerosene and diesel with renewable energy, taking carbon dioxide out of the air with direct air capture, and then running that through some catalyst technology and converting that into a direct replacement. Again, that's very expensive now, but if we incorporate that into a precinct, we use waste heat to assist with direct air capture of carbon dioxide, and we do it on a large scale and utilize some surplus renewable electricity, then we can bring that price down to something that's competitive with the fuel that we have now. So one concept I worked on was how this could all fit together in a hospital. So hospitals are a great example of combined heat and power needs. They have large heat loads for steam, for sterilization, for example, and air conditioning in the building, as well as electrical loads for lighting and equipment. And they also need backup power, which is conventionally done with a diesel generator, but that can be replaced with a fuel cell. Microsoft's doing that for data centers. Again, the problem with all this is just putting in a battery to be used not very frequently, or a fuel cell to be used not very frequently, quite expensive. But if we oversize the battery a bit, then it can help with electric vehicle charging and grid stabilization. The fuel cell can do load shifting. We can use the oxygen for keeping people alive with ventilators. We can use other power to X technology and make hydrogen peroxide, for example, to use as a disinfectant. We can feed in surplus hydrogen into the gas network to decarbonize that and use that as an industrial feedstock for things like e-fuels, as I was talking about, to fuel helicopters evacuating people. There's all kinds of opportunities with power to X, and it's a little bit like magic, feeding electricity in and getting all kinds of stuff out. One of the things some of my friends and colleagues are working on out of UNSW is turning brewery wastewater into hydrogen. And then there's another company in America called the Air Company that's taking carbon dioxide and hydrogen and turning that into ethanol and making carbon negative vodka, which is, as a Russian, something that's exciting to me. So that's just a little bit of an insight. I'd like to give a shout out to some of the people I collaborate with, the Part Cap group at UNSW, Rosa Mal and Diane Raman, we collaborate with on the Power to X pre-feasibility study for the New South Wales government, and the ARC Industrial Transformation Training Centre for the Global Hydrogen Economy. And I'm here at the Newcastle in collaboration with UNSW under the New Alliance, and some of my flow battery work was done with the German-Australian Alliance for Electrochemical Technologies for the Storage of Renewable Energy, otherwise known as CENELEST. That's all for now. I'll leave it open to questions to see what you guys want to hear more about, and I'll pass it back to Nicole to facilitate that.
Thanks so much, Nicholas. Yeah, I had asked everyone to send their questions through towards the end, which everyone's obeyed nicely. So hopefully we'll see them start to filter through. I know there'll be a lot to talk about, but this first one actually is a great question from Michael Poulton to you, Nicholas. Is there a solution for hospital waste of food and organic in your medical model?
Yeah, so biomass is actually a great way to reduce the cost of producing hydrogen. Biomass electrolysis has a lower energy input for creating the same amount of hydrogen. So that's why, as I mentioned with the brewery wastewater, if you change the catalysts, yes, you can use organic material and it can actually be economically beneficial.
Yeah, it sounds amazing if you could just get everyone lined up in the right order, in the right spots, which is, I guess, the idea of a precinct and co-locating. Both of you in your processes and research have mentioned that there still is, you know, to completely decarbonise these processes, a part of carbon capture required. I thought I'd bring that up straight away because I know that's something on everyone's mind. We have heard so much that, you know, this is really expensive technology, it's not proven. Have you guys got thoughts, both you and Jessica, on that?
Yeah, carbon capture is, so what Jessica and I are interested in, I guess, is the deep decarbonisation challenge. So solar, wind and batteries are the answer to lots of things, but not everything. There's still industrial processes that have carbon emissions or use carbon as a feedstock. So my work is looking at including direct air capture. So it is a carbon neutral concept, but there are other processes. I'll let Jessica take over.
Yeah, so exactly what Nick said about after deep decarbonisation, what's left over is what you mop up with these technologies. The technical side of carbon capture has never really been a major issue. So it's used in industrial processes. They use amine solutions to capture carbon dioxide in things like ammonia generation because they can't have that in the reactor. So it's used technically and they make a pure carbon dioxide stream. The problem with the challenge with carbon capture and storage has always been you spend all this money on capturing and storing something that no one makes any money from. So it's never been pushed forward. It's never had that commercial uptake or interest that it needs to actually go through a technology development. So it's really it's an environmental solution, not an economic solution. And that's part of the reason why it hasn't gone through this major uptick. One of the things that I'm more interested in is also not carbon capture and storage, but carbon capture and utilization. So making useful products from a waste product is where we need to be at. Ideally, that will be stable products, so it takes the carbon out of the carbon chain. But if you're doing direct air capture, as Nicholas does, then it's just sort of cycled around. Direct air capture is still under development, but I've got some colleagues at the CSIRO Energy Centre who've been working on that for many years, and it is coming along, but it's just not financially viable without more momentum. And I think we're getting there because people don't want to buy products anymore that have a carbon footprint. And all of our trading partners, their partners are looking at these scope 3 emissions. So looking at how their products are used and where the emissions are going and coming from. The majority of our trade partners have committed to net zero, as I'm sure most people on this chat are sort of well aware of. So I think the drive for carbon capture is increasing. I think we need to be wary because it is sometimes put up as a band-aid solution. So let's just keep doing what we're doing now and we'll stick carbon capture on the end and we'll be fine. But I've never really thought of that as a strong solution because you still need to keep mining, you still need to keep storing the carbon dioxide. It's an ongoing process that doesn't really have an end, and it's just not doable on the scale that we're doing it at the moment. So once we've gone through this deep decarbonisation, then those technologies, they're really going to come to the front and they're going to be really important to actually get to a true net zero outcome.
Thanks, Jessica. There's a couple of questions that have come through. It's probably for all three of you, but potentially Sam. You know, there's some amazing innovations and technology coming out of the university. Have you guys been aware of plans to, I guess, keep that innovation and the jobs that are associated those with in Australia?
So yeah, I'll jump in.
I thought that was for Sam. Sorry, I was waiting for
Sam looked like
Sam.
she was maybe going to talk, but you go, Nicholas, and we'll come back to Sam.
Yeah, so it's a shame a lot of these technologies that we invent in Australia go overseas, but the New South Wales government's quite committed to commercialising or helping develop some of this technology from New South Wales universities. And I personally know of a consortium of solar and flow battery manufacturers that are interested in making a factory in Newcastle, actually. The key for a lot of this is offtake, so demand, so someone to buy the equipment and buy the output, which is why I've looked at healthcare and defence, for example. The federal government is paying a lot of money to secure our insecure fuel supplies, but that largely amounts to just building bigger tanks. The Europeans are actually just getting on with this and actually building some of these technologies up to scale to produce renewable fuels. So yeah, government has a big role to play in facilitating the early development of this, because it's quite expensive in the beginning.
Sam, do you want to chime in on that too?
Well, Beyond Zero Emissions has just had some modelling done on the jobs that we can create in the Hunter from our renewable energy industrial precinct, and it's pretty positive. I won't talk about it too much, but it's a pretty big win for the Hunter, and I know that where I'm sitting in the clean tech space at 1804, there's new people starting every week. The businesses that are starting up here are growing really fast. And the battery factory at Tomago is going to employ quite a lot of people. And then we've got the battery factory down in Cardiff. So, and then today, with the announcement of the hydrogen project, which is still pretty high level, but there's a whole stream of jobs there. So it's sort of answering our modelling pretty well.
Thanks, Sam. Just going back up the feed to an earlier question for Jessica, there was Wendy, I believe it was, had asked, even in the 100% reduction of renewable energy version of producing steel, were there going to be other heavy metals emitted into the atmosphere? Didn't seem to be on your slide.
Yeah, you won't have the same. So the blast furnace is where a lot of emissions happen that have to be cleaned up from steel making. So it's a little bit different with the direct reduction furnace, but it would still, the flues that come out of that, they have to be sort of reused internally in the process and then cleaned up. So you still have to do some sort of cleaning with it. But it gets rid of the heavy metals that are in the coal process. So it's just what's involved in the iron ore and whatever the gang has in it as well.
Thank you. All right, everyone's a bit quiet today. We haven't got as many questions coming through as usual.
Nicole, I saw one, I think from Freya Leonard, about what's the land footprint to produce a single steel smelter using green hydrogen?
I don't have the numbers for it yet. But I had, so last year, so our undergraduates do a design project here at the University of Newcastle, and last year we did green steel. And so they were doing a project trying to size something that was doing that 70% sort of hydrogen replacement, and they were locating it out at the Pilbara. I can't remember the exact numbers, but it was a significantly large solar field. I think probably when you start looking at the land area for solar and for industrial precincts, you need to look beyond just solar and diversify that renewables output. because if you just have it in the middle of the day, then you have to have a lot more hydrogen storage. So you need to have a more stable output. So having something that has sort of offshore wind maybe, as well as solar, as well as grid management with batteries, to have a more stable output will actually reduce the area that you need overall and also reduce the storage requirements. But I don't have the numbers. That would be a good one to have offhand, because I'm sure I'll be asked that in the future. So I might do some calculations for you.
I think it was a different Wendy from the last one, but I've got another Wendy here who has asked whether we had the salt caverns for large scale hydrogen and what other storage.
Yeah, that's the most promising way to store large amounts of hydrogen is in existing salt caverns. We do have them in Australia. It's tricky to try and match that generation, storage and use. It's the same issue with carbon capture and storage, actually, where you're generating the CO2 is not necessarily where you need to store it, as well as with the hydrogen where you're generating it. So you really need these things to sort of line up and come together for it to work. But if you can distribute that renewables input better and have a flatter curve for the industrial process, then that will reduce the amount of storage you need. So that's sort of what we would need to do in somewhere like the Hunter, because I don't believe we do have naturally occurring salt caverns here.
Yeah, and actually just still on hydrogen storage, have we, has either of you done any research into different storage options and their efficiency in terms of, you know, weight? Because obviously the canisters are very heavy as well.
So I have looked into, oh, sorry, Jeff.
You go.
I've looked into it a bit. And I was down in Smart Energy Council last week and heard a presentation about Arden Underground, which is actually repurposing technology used to drill access shafts for coal mines to create basically artificial rock caverns. And they can do that at a price point competitive with rock caverns, which is pretty cool because, yeah.
That's good news.
Yeah, especially for this area. So I really like that as a neat solution because, yeah, as Jeff said, salt caverns are challenging in Australia. There's a few different sites, but none of them are in New South Wales.
This one's a pretty broad one, and Sam, probably for you. You would have touched on it at the beginning of your presentation, but what do you estimate to be the key industrial elements of a renewable energy industrial precinct? Right up your alley.
Look, I actually think we've got it in spades in the Hunter, and that is the ability to do what we're doing now, talk together, listen to each other, bring in everyone's expertise. It's like an ecosystem. It's complicated. It's an ecology, and to be able to have these discussions, to be able to keep talking and collaborating, and that was what, you know, when I watched the panel discussion again that we had at the Hunter Innovation Festival, that is what everyone talks about as one of our strengths, is our ability to talk, listen, collaborate, and it's a bit of a radical example. But one of the best examples of collaboration in the Hunter is the Hunter coal chain, where all of the companies are actually competitors, but they all work together to get their coal on these trains that, you know, end up. So it's quite amazing that they, you know, they come from these different mines all over the Hunter, they go on the train, they go through the port, and they end up in their customer destination. But before that happened, we actually had a really inefficient process in the Hunter, and there was, you know, always hundreds of ships offshore, there was bottlenecks, people were waiting, but that we can talk together, we can design, we can use efficiencies, we can use waste streams, we can, that's the strength.
Thanks, Sam. Yeah, definitely very good ideas for the Hunter to be here. I'm just we don't have too much long left, but I want to throw this question to all three of you. I think it's a good one. It's maybe a bit tough, but in an ideal world, if you could build something this year that would be up with approvals and capital ready, what would you focus on?
Sam, look like you want to talk?
Go, Sam.
Well, I just get started. Yeah, if we had all our approvals, I kind of think we have the groundwork of all of a base of companies that want to work together and get the site. And yeah, I think what we'll end up producing here in the Renewable Energy Industrial Precinct is batteries, electric vehicles, but like heavy, like industrial electric vehicles, and mining equipment, and metals. Like, you know, I'd love to see all of Australia's precious minerals that we mine and send overseas just processed here. Like, so that would be what our precinct will, yes, build on our strengths and what we're already doing and just do it cleaner and better and smarter.
Thanks, Sam. Jessica, did you want to jump in with your one thing?
I think it'd be great to see some pilot work in decarbonising the industries we already have here. So things like Tomaga aluminium, very heavy emitter, but they also use a lot of electricity. So part of that could be decarbonised and form part of a renewable energy precinct. So if they're using that known supply of electricity, that's a big part of the job done. We've also got some manufacturers holding on in Newcastle which need more support in helping them to decarbonise in places like Orica on Kooragang Island that are producing ammonia. So they make ammonia for explosives for the mine. So they're a Hunter Valley sort of explosive manufacturer. But ammonia is hydrogen rich. The hydrogen they get from that is actually from methane at the moment, but you could do it with green hydrogen. Up to a certain extent. Like I said, with some industrial processes, it's not a simple one-for-one replacement, but they could certainly decarbonise a large portion of that. And ammonia is really interesting because we have a large port here. Ammonia is easy to transport and get around, and it's also been earmarked as the future of shipping fuel. So to ship globally around the world, we need a new type of fuel that is zero emission, and ammonia could be that fuel. So that's what the shipping industry is investing in heavily at the moment. And we have a deep port. We have ammonia generation facility already. So I would love to see us decarbonise the industries we already have, and then use that as sort of a showcase to start growing new industries and buying into that renewable energy precinct idea.
Beautiful. Thanks, Jessica. Nicholas, did you want to weigh in your one thing as well?
Yeah, sure. It'd have to be the renewable hospital concept for me. My brother's a junior medical doctor, and the local health district here is recently committed to a net zero by 2030, which is really worth a round of applause on their behalf. So I would love to create a net zero hospital and support the decarbonisation of the medical supply chain. Yeah,
it does sound perfect, doesn't it? We just have 2 minutes left. We always get run out of time here. I'll go over to Sam quickly. I know she has some parting words. There's also been a question about whether all of this amazing work in the Hunter, we're talking to other groups around the country like the Latrobe Valley and Gladstone. So maybe touch on that too, Sam, if you get a sec.
Absolutely. I just want to say thank you to Jessica and Nicholas. And I just, there was a question about the Hunter Jobs Alliance. Beyond Zero Emissions isn't part of the Hunter Jobs Alliance, but we're working very closely with them. I'm actually having lunch with the coordinator tomorrow, part of my job, lunching with cool people around the Hunter. But Warwick also spoke at our industry panel, and we're very much aligned, working very closely together. And yeah, I also just want to thank everyone here for participating. It's great to have a window and look in at the University of Newcastle and see what's happening there. It's a great institution. Thank you very much, everyone.
Thanks so much, Sam. Just to round out that last question, and the answer is yes, we are doing a lot of work in the Hunter. We're doing a lot of work in Gladstone and starting to look at some of those other regions as well. But a REEP is an idea, right? A renewable energy industrial precinct is an idea that we would hope would be relevant to all of those, to heavy industry areas around the country. So thanks again to everyone for joining us. I will make sure that I post all of the resources, presentations and recording onto the Beyond Zero Emissions website on the events page. If you love what we're doing and like to support us, please always jump in and hit that donate button that's across the site as well. Your support is what enables us to do all the amazing work we do. So thanks again to everyone, and we hope to see you next month. Bye for now.